Good morning, Year 10s. How's it going, guys? Right, today is going to be a rapid lesson. We're going to go through the holiday homework on redox. Really important for the test that you're sitting tomorrow. Yeah, so make sure that you've gone through this, you've completed it, and you've understood what's happening. But I'm going to crack straight on with this. I'm going to share my screen. I'm going to try turning off my camera. Now my laptop crashed. So what I'm trying to do is if I click onto my notes and then disable the camera, I think it might not. Fingers crossed. Don't crash, don't crash, don't crash. Yes, we're there. Okay, cool. Can you guys just confirm that you can still hear me? I'm just going to make sure that the other, there we go. Amazing. So that should be all running. If you want to improve the quality, if you go to the little cog at the bottom, you can improve it. Right, I'm going to close that. My chat windows. Hi, Callista. Hi, Julius. Hi, Lauren. Hi, Owen. That's great. Oh, Zina's now here. Ooh. I'll add you to the register, Zina. Okay, right. Let's crack on. Let's crack on. Okay, holiday homework, holiday homework. Okay, so I gave you a redox homework, guys. I'm going to be super quick with this. You can mark your own. Okay, name the ore used for the source of iron. Hematite. Got to know that one. Hematite. Yeah. If you've put magnetite, I don't really want you to use it. Edexcel don't recognize magnetite, so just ignore that one. But yeah, hematite is the one that you need to have your 1 mark. What is the formula for aluminium oxide? So aluminium is +3. We get this from the periodic table. Let me just quickly show you. GCSE table. Find aluminium. Give it 1 second while it sorts itself out. There we go. So aluminium is there. It's in group 3. We remember +1, +2, +3, +3, +4, -4, and then -3, -2, -1, and no charge at all on the noble gases because they have a full outer energy level, so they don't react. So aluminium and then oxygen is O2-. Again, from the periodic table, it's in that column. Cross and down, a bit of an X factor job, and we get Al2O3. Tick it if you've got it. 1 mark. Next, what is the name given to the reaction involving reduction and oxidation? It's called a redox. Moving on. Why does this equation represent a reduction reaction? Because reduction is gain of electrons. We get that from oil rig. Oxidation is loss of electrons. Reduction is the gain of electrons. Gain of electrons. And aluminium, Al3+, gains 3 electrons. Winner. Next, identify the substance that is oxidized in the reaction and give a reason. So we're looking at the chemical reaction here, and what we can see is that the person gaining oxygen is carbon. So that one is being oxidized. So the substance, identify the substance oxidized. Carbon is oxidized. Carbon is oxidized. Reason, it is gaining oxygen. Gaining oxygen. There we go. 2 marks. Now, just to quickly mention, well, if that's the case, what we're doing is this reaction here is the extraction of hydrogen gas. Hydrogen gas is a great fuel used for rockets. And just to let you know that this is being oxidized, but is therefore, it's nice just to mention this. I'll change my color for this, green. It is therefore the reducing agent. It's nice to mention agents as well. Itself being oxidized, it's really tricky, that hard to wrap your head around. I totally get it. But you can see carbon is oxidized, carbon is gaining oxygen. I like it. 2 marks. Moving on. By the way, you can see I've given you the years of each of these papers as well. Okay, next one is thermite. Gotta love thermite. So we've got what is meant by the term exothermic. 1 mark. Change back to red. A chemical reaction that releases heat energy to the surroundings. You can decide whether or not you want to give yourself that mark. I'd much prefer it if you just, lots of students tend, the common mistake here is that students just go, releases energy. That's all they say. It's not enough. Looks like I've put releases energy, heat energy to the surroundings. If you've put a really basic answer, please just make the amendment and don't give yourself that one. I don't know what's going on in the chat. Oh, okay. Hang on one sec. I like it. That's better. Oh no. I've got loads of people who are interjecting. I apologize, folks. Sigh. Yeah. That's okay. They have now been, do we lose marks if we say it just produces heat? If you say a chemical reaction that produces heat, I don't mind, Julius, you can have it today, but I would definitely say make the note of what they want. Trolls, I know, trolls, I know. I've removed them all now, folks. Do we lose a mark if we do not mention to the surroundings? I'm going to say not today, Zina, but as I said, I need you guys to learn that definition for your GCSE. It comes up a lot in multiple topics as well, so it's worthwhile adding it. Yeah. What does the reaction suggest about the reactivity of aluminium compared to iron? Right, so aluminium is more reactive than iron. Yeah. It suggests aluminium is more reactive than iron. Now, that's only one mark. We need to say a second mark, and then we need to explain it. And the reason why is because aluminium displaces the iron from aluminium oxide. Aluminium displaces, that's the key word. Yeah, displaces iron. Aluminium displaces iron from iron oxide. It's nice to do that. From Fe2O3. It's always nice to do that. Formula of rust as well. Right, next. Oh, sorry, my laptop's taking a bit of time. There we go. Which element is oxidized in the thermite reaction? So who's gaining oxygen? Aluminium is being oxidized and iron oxide is being reduced. Aluminium, Al, is being oxidized. You can see how common these questions are. Folks, it's designed to be repetitive. Aluminium is being oxidized since it gains oxygen. I like it. You could also say, by the way, loses electrons. So that's which element is oxidized. Aluminium is oxidized. The one being reduced, making aluminium oxide. Yes, since it gains oxygen. Yes, that's absolutely fine. Yeah, that's making aluminium oxide. That's totally fine, Ian. Absolutely fine. Yeah, the Al is becoming aluminium oxide, so it is gaining. Yes, totally fine, Ian. Yes. Next. Okay, so the thermite reaction is used to join railway tracks. It's nice to see EdXL, June 2014. Really nice that. The reaction mixture is ignited and molten iron pours into the mold. The mold is removed and the iron solidifies, creating a joint between the two railways. Explain why iron produced in this reaction is molten. The reaction is very exothermic. The reaction is very... It's nice to actually tell you that. By the way, temperatures in excess of nearly 2,000 degrees Celsius, it be crazy hot, is very exothermic. What that, by the way, that is the mark, just so you know. I just always like to give them a little bit extra and say, so temperature reached is higher than the melting point of iron. There we go. It's just nice to put that, but the reaction is very exothermic, does give you the mark. Name 2 substances needed for iron to rust. We need water and we need oxygen. 2 marks, nice and easy. Okay, iron objects can be prevented from rusting by coating them with zinc or tin. Some of the objects may be scratched when used, so coating may come off. Use the order of reactivity to suggest why coating objects in zinc is more effective than tin. So the tin layer is purely a protective barrier. Yeah, if you cover something in tin, which symbol is rather odd actually, comes from the ore of stannous, I think, something like that, or I can't remember what tin is. I think stannous, or something like that. Stannonite. Oh, I can't remember. Anyway, so the tin layer is purely protective in terms of it being a coating. And when it's scratched, it'll then rust. Yeah, it would rust at that point where the scratch would happen. And the coating would then flake off. But coating it in zinc is much better. The reason being, so 3 marks. First mark is for saying zinc is more reactive than iron. But tin is less reactive. So when zinc layer scratched, zinc will react with the oxygen first. It's called preferentially, really, stannum. Oh, look at that. Thanks, Zina. Appreciate that. Stannum. Came from the guy who discovered the tin ore. His name was Stannus. Yeah, I think. Is it stannamite? Stannamite? Something like that. The ore. When zinc layer scratch, zinc will react with oxygen first. By the way, it's actually more than that. In reality, here's what happens. Yeah, if I have a piece of iron metal, yeah, what will happen is the iron will react with oxygen, react with O2 to form patches of rust, Fe2O3. But if I have zinc nearby, yeah, if zinc is nearby, the zinc will react with the iron oxide to form zinc. Sorry, I'm just gonna, there you go, to form zinc oxide and iron metal. Balance the equation, 2 irons, 3 oxygens, 3 oxygens, 3 zincs. There we go. I think that works out. So it turns, now just to put that in terms of electrons, what's happening here is the iron 3+, which is the iron in rust, is going to gain 3 electrons to form iron metal, and the zinc metal is going to lose 1 electron, oh, actually 2 electrons, I apologize, to form that. And what happens is these equations now come together. So the zinc is providing the electrons for the iron to turn back into iron. This is what's happening in terms of electrons. Yeah, and then you can balance these equations and add them together. It's quite nice to do this. So the electrons need to cancel. Yeah, the electrons here need to cancel. The common denominator is 6. So times that one by 2, 2, 6, and 2, times this one by 3, 6, 3, and 3. And notice, look, they actually go together in the equation. Yeah, there's 2 ions in there. Yeah, there's 2 ions over here, 3 zincs here, 3 zincs here. It's quite cool, that. And then the electrons cancel out, and then the equations go together. So, and then the final equation would be 2 Fe3 pluses are reacting with 3 zincs to produce 3 zinc 2 pluses plus 2 Fe's. There's the combined redox equation. It's quite nice, that. Next, right. Okay, this was a really hard question from Edexcel. Explain one safety precaution that should be taken when adding the dilute acid. So, by the way, pieces of equipment, this weird piece of equipment there is called a tap funnel. It's just nice to mention stuff like that. It did come up in one paper. It's called a tap funnel. I know it's a funnel with a tap. And before lighting the unreacted hydrogen gas. Okay. So the first thing is that acids are corrosive. Acids are corrosive. Wear gloves. Yeah, wear gloves or goggles. In fact, you should actually wear both, just so you know, because you're not going to throw it in people's faces, but gloves and goggles is the right choice. Either, that's 1 mark, folks. Yeah. Now, lighting the hydrogen on fire, right? So we know that hydrogen is explosive. Yeah, we know that the hydrogen is explosive, and before lighting the unreacted hydrogen. Yeah, we want to make sure that they've, so hydrogen H2 is explosive, light in fume cupboard. Does everyone know what a fume cupboard is? We've got one in each of our labs. Yeah, they're the big cupboards with the glass door on. I don't know if I've actually used one with you guys before. They're usually for toxic gases, but if there's going to be an explosion, you want it to be in a cupboard. At least it's going to offer some kind of protection. We've got one of these in every single one of our labs. Yeah, definitely. State the observation that would be made when the dilute sulfuric acid reacts with magnesium. Right, what are we going to see, folks? So when the magnesium, when the acid, we're going to see A, we're going to see fizzing. Yeah, we're going to see bubbles. Top answer. Yeah, we're going to see bubbles. Yeah, don't put we see a gas. Gases are invisible. You're not going to see them. Yeah, we're going to see bubbles or fizzing or effervescence if you can spell it. The next thing is the magnesium will disappear. Magnesium will disappear. It will disappear over time. Disappear. There we go. Next, state one observation that could be made when hydrogen is passed. This is really hard. Right, now this one requires a bit of conversation. So we've got a tube here, folks. And in that tube, this is really hard. In the tube, we've got copper oxide. Now, just to show you what copper oxide looks like. Yeah, because unfortunately, Edexcel require you to know copper oxide because it has a very particular color. It's black. There we go. So it's black. There's copper oxide. Oh, copper 1 oxide. That's weird. Ignore that. Copper 2 oxide is black. Yeah, that's super important. Ignore all the other stupid colors. It's the internet being rubbish. So copper oxide, copper 2 oxide, which is just CuO, is black. It's jet black. Jet, by the way, comes from the rock jet. Which I'm pretty sure might contain copper oxide, actually. Anyway, so it contains copper oxide. Now, what we're going to do is we're going to pass hydrogen gas over the surface. Now, hydrogen gas, as we all know, is more reactive than copper. It's in the table. It's the one above it, reactivity series. Yeah, and there's hydrogen. So the hydrogen is above copper. Yeah. Now, if hydrogen is above copper, what that means is it's going to displace it. The copper oxide is going to react with the hydrogen to form water and copper metal. What that means is the observation that we're going to make at the end of this, we're going to have a pink metal left behind. It's going to be, it's like pinky orange. Ah, that's actually quite a good color, actually. Yeah, you end up with pink metal. Yeah, pink copper metal. Cu solid. Yeah, and you just have to know that one. That copper metal is pink, just to show you this. Copper metal. I know everyone's going to say it looks orange. I get it. But it is pink. When you have pure copper, it would actually look at the end of the experiment. It would look a bit like that, to be fair. Yeah, there we go. Look a bit like pink copper metal. So the observations here state one observation that been made when the hydrogen is passed over the heated copper oxide. A solid pink copper metal will appear. Pink copper metal. Copper metal will appear. Oh, hang on a minute. No, black solid turns pink. That's the observation. Black copper oxide turns pink. That's the observation. Yeah, pink and shiny to boot, because it's actually a metal. Right, next. Complete the word equation for the reaction. So magnesium and sulfuric acid. I'm going to get magnesium sulfate. Yeah, magnesium sulfate. And metal plus acid, salt and hydrogen, MASH. So I'm also going to get hydrogen gas. Then we get copper oxide plus hydrogen. I'm going to get copper and water. That was hard, that. Trickier one. Unfortunately, if you didn't get the picture above, then you probably weren't going to get that question. It's clever how they tied those two equations. As I wrote orange brown. I will let you have it today, Zina. Definitely, you can have it. Okay, so put the two half equations together. Right, so there's the split, and the electrons are on opposite side with the same number. So we just put them straight together. Fe plus lead 2 plus goes to Fe 2 plus lead. Nice. That's nice and easy. This one, a bit more challenging. There's the divide, but this one needs 3 electrons, but this one's only giving us 1. Times that one by 3. 3, 3, and 3. Put them together. Final answer. Aluminium 3 plus 3 potassiums goes to 1 aluminium and 3 potassium 1 plus ions. Winner. Take it if you got it. 1 mark for each one. Next, calculate the averages. This is worth 2 marks, folks. It's worth 2 marks. This is why the total is out of 29. The average, of course, for the top one is 0.0. Average for the second one is add them all together and divide by 3. 0.7 plus 0.5 plus 0.5 divided by 3. Average, 0.566. Oh, 567, 3 sig fig. If you put 57, I'll allow it. Next one, this one's important. This one is a mark all on its own. Guys, there's an anomaly. So if you ever see anomalies in data tables and you're calculating an average, you ignore it. Students might ask, how do I know that's an anomaly? It's actually really close to the next number. It's way too high. So we're going to delete that one. So we're just going to add that and that together and divide by 2, which means it's going to give me exactly the same number. These guys are all similar. So we've got 1.7 plus 1.8 plus 1.9. Oh, the average is 1.8. Of course, it is the middle number. Next, 2.5 plus 2.5 plus 2.3 divided by 3 gives me 2.433. That'll do 2.43. Next, still only a 0.2 difference instead of a 0.5 difference. Yeah, so they're all similar enough. So 3.1 plus 3.1 plus 2.9 divided by 3, and I get 3.03. That's interesting. So just to let you know, that one there is a single mark, and then all the rest of these are 1 mark. Total 2. So you need every single one of these correct to get that 1 mark. If you get any of them wrong, you drop 1. Right, guys, you can now fill in your data table, your homework table. It's out of 29. You can add them in. If you can do that by the end of the lesson, that would be grand. Right, and guys, I'm now going to crack on with my lesson today. Okay, so today's lesson, we're doing 3 learning objectives, and they're all understands. So understand iron extraction, understand titanium extraction, and understand alloys. Now, in reality, the understanding of these is purely from a chemistry reduction and oxidation perspective. It's just, you don't need, so key point to make here is at EdXL, at IAL, the International at IGCSE, you require no knowledge of the process itself. So my title now is Iron Extraction. Iron Extraction. Iron Extraction. Is everyone still there? I know that the chat window is still there and running. Just going to quickly check my sheet again. Why not? Oh, look at that. Zina smashed it. Julia smashed it. Well done. Superb. So iron extraction. Now, iron extraction, just to tell you, by the way, that copper and I believe zinc is also extracted this way. Yeah, so ion extraction, the method used, the method is called the blast furnace. It's called the blast furnace. And here's what it looks like. Now, you don't need any, you need no, for Edexcel, IGCSE, you do not require any knowledge of this particular picture. But what you are expected to know, so no specific knowledge of the blast furnace of BF, best friends, no specific knowledge, but need understanding. The reason being is they're going to give you this, and they're going to give you bits of information from it, and you're expected to use your understanding of metal extraction to explain what's going on. But you do not need to know any like the temperatures or input and outputs. You just need to be able to use what they give you to explain it. Okay, so let's be quick. So in the blast furnace, so number one, you can see what's going in at the top. Now it says iron ore in the form of Fe2O3, and we've got coke. Now coke is actually pure carbon. And then fluxes, which is limestone. Now, you don't need to know these. And so I love what they call it. I don't like the word fluxes. I'm going to get rid of that and just put limestone. Can you make a quick nota bene for me, folks? This is something I do need you to know for GCSE, and it's very important. Calcium carbonate, CaCO3, is called limestone. Now, just to point out that this is a very important resource for mankind. We use millions of tons a year. And it was deleted from Edexcel a good few years ago now, and it annoys me because they still ask so many questions about it. So I just need you to recognize that calcium carbonate is limestone. Just going to put that in a nota bene box. There we go. Okay, so key facts we need to know about metal extraction. Facts. Facts for metal extraction. Number one. We always, there is one exception, but I'll talk to you about that another time. We always need high temperatures. So, and this is one of the main costs. Yeah, we always need high temperatures. Cost is fuel to heat. Yeah, people often say, you know, oh, heating costs money. No, heating doesn't cost money. What costs money is the fuel to burn to provide the heat. Yeah, you don't say it's one of those really awkward things there, because students make silly mistakes simply by saying, you know, oh, energy costs money. And I'm like, it's the fuel for the energy that costs the money. Okay, so we need high temperatures. Let's just show how this is the case. 1900 degrees Celsius. That is crazy high. It's really difficult. I can't do that in school. You need a furnace to be able to hit those kind of temperatures, and I can't do that in lab. And I certainly haven't built myself a blast furnace yet, or a mini furnace to be able to do that. But that's crazy high. So where does that heat come from? Well, it comes from the carbon. We added carbon to the blast furnace to provide the heat. So what happens is, by the way, look what else goes in. Hot air is also going into the blast furnace, which provides oxygen. Yeah, the O2 comes from the air. And what happens is the carbon burns in oxygen to form carbon dioxide. This is very exothermic, gives us lots of heat. Takes the temperature up to about 900 degrees Celsius. Now, what also happens, and this is the weird bit, the carbon dioxide actually reacts with more carbon to produce carbon monoxide. And I'll balance that. There you go. Now, this is also exothermic. And this takes the temperature up to about, the first one takes it up to about 1,000. And then the second one takes us up to 1,900. Crazy hot. So 2 equations for the heat, and it's because they're burning. Yeah, these are combustion reactions. And the great thing is this, the output of this is carbon monoxide. And that carbon monoxide is my reducing agent. Yeah, it is the reducing agent. This is what's reducing agent. This is going to steal the oxygen from the ion. So the Fe2O3 now reacts with carbon monoxide to form carbon dioxide and iron. So, and that is all you need to know. Balance the equation, 4 oxygens, eek, this isn't going to work out. I'm going to need to put a 3 there and a 3 there. I think that now works actually, doesn't it? Yeah, 6 and 6. 2 ions here, 2 ions here, 3 oxygens, no. And 6 oxygens in total, 6 oxygens in total, 3 carbons, 3 carbons, it all adds up. Cool. And this is the reducing agent. It's also what's being oxidized. Yeah, this is the red agent and is also being oxidized. Yeah. So it's just nice to explain what's going on. And that's all you need to know. The temperatures are high enough to produce molten iron as well. The iron literally pours out in the form of a liquid. And this is a continuous process. These machines are about 9 stories in height. This is 9 stories tall. Yeah, and stories in terms of buildings. Yeah, 9 stores, nice. 9 stories tall. It's massive. And they run for 10 years continuously. They never turn them off. They just keep feeding in what they need. They feed in rust, iron oxide, they feed in hematite, they feed in carbon in the form of coke, and they feed in loads of limestone as well. If you're interested in what the limestone is doing, just for those people who like the extra, so the limestone goes in, and the limestone actually reacts because it's a base. Yeah, it's a base because metal carbonates, metal oxides and metal carbonates are all the opposites to acids, they're bases. That's going to react with sand, and sand is acidic. Yeah, it's an acidic compound, and it reacts to form calcium silicate and carbon dioxide. And that comes out as a liquid. And it's actually given a rather awkward name. It's called slag. Yeah, I know, calcium silicate, common name slag. And it was given that name because it used to, see, if you notice, the slag is floating on top here, and it pours out as a liquid. And that then gets buried in the, it's actually sold now to make roads. Sold to make roads. That's what the, to make roads. That's the black chips make road surfaces. That's the black chips that you see in the road. What fuel are they using to keep it hot enough? Carbon. Loads and 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 loads of carbon in the form of coke. Boatloads, Ian. Boatloads. They just keep feeding it. These provide the heat. This is the heat of the reaction. Yeah. And then that one's just to remove sand, because sand clogs up all the pipes, you see. So they have to remove it. And then at the bottom, molten liquid iron comes out, Fe liquid, because it's way above its melting point. Melting point of iron is about 1600, so about 300 degrees above that, so it pours out in a liquid. Cool. So that's the blast furnace. As I said, this one's not needed for GCSE, but it's nice to have it there. It's needed for A-level. And then all of these are needed just to be able to explain the term exothermic at Edexcel and explain the reduction process. By the way, another fact, any metal extraction reactions, this is fact number 2. Yeah, fact number 2, which I'll switch to red again. Fact 2 is any metal extraction process is called a reduction. The reason being is because we have it now, even though we know it's actually a redox, yeah, we know it's actually redox because there's always someone being oxidized if someone else is being reduced. But because we're after the metal, we tend to call it a reduction. So just so you know, it's just an extra bit for you. Okay, so that's the iron, that's iron extraction. Yeah, and by the way, we also do exactly the same process for copper and zinc. Yeah, anything below carbon, we will throw in the blast furnace. Yeah, I could swap this for copper carbonate. I could swap it for copper oxide. I'm making copper each time for that. At the bottom, I will get molten copper out the bottom. Could also do this with zinc oxide, all because carbon is more reactive than that. You can do this process with any metal below carbon in the reactivity series. Okay. Next, right? Titanium. Gotta love titanium. Titanium. I'd usually, if we were in class, I would have put the song Titanium on. Titanium extraction. Okay, so we absolutely love titanium. The reason being is it's got some key properties. Number one, it's got a high melting point, higher than iron. High melting point. It's also crazy strong, stronger than iron. Yeah, it's also crazy strong. But in fact, its top property, similar to aluminium, it doesn't rust. It's corrosion resistant. This is why we love, if you had, you know, by the way, this is why, I'm sure you guys probably know this, but if you ever have a replacement bone, bone replacements, yeah, images. Oh, blimey. Oh, that's really interesting that they've gone for teeth replacement. Interesting. Let's go for, rather than teeth. Oh, don't want the word graft. Bone replacements. Yeah, let's go for joint. Let's do joint replacement. Joint replacement. Right. Now, whenever they do any hip replacement, any hip replacement, knee replacement, elbow replacement, hip replacement. I think I've already said hip replacement. They only ever use one material, and that's titanium. They actually use two materials. One of them is titanium, and the other, of course, is PTFE, polytetrafluoroethene, which is a plastic designed to give it some lubrication. It's very, very slippery plastic. But whenever they replace any bones or joints, the only material they ever put inside people is titanium. And they do this because titanium doesn't rust. Yeah. And this is the top property of titanium. Yeah. Used in joint replacements. Joint replacements. Because what you don't want to have is to put a piece of metal inside somebody and then have it rust. That's a really bad idea. Stents. Yes. Gayatri. That's why they use it in hospitals, right? Like in clips and stents. Yes, and stuff. Yes, absolutely, Gayatri. Spot on. Yes, they use it in all kinds of cool things. Any material going to the body tends to be made of a type of titanium. Yeah, most of the time pure titanium to boot. Stent. Stents are actually rather complicated. Because it's actually a shape memory alloy. It's a really cool material. I actually have a stent. I was given one by a student's dad once. Amazing. I'll bring it into school and show you guys. It's awesome. Anyway, but yes, it's actually got titanium in it. It's kind of cool. So titanium is high corrosion resistant. We love titanium, but the problem is it's very expensive. And the reason being is due to extraction. So how do we extract? How do we extract titanium, Ti, solid metal? Right, the process is actually called the Kroll process. You don't need to know that, by the way. It's just cool to do, cool to know. It's called the Kroll process. Now, titanium, I'm going to do this as a flow chart. Yeah, flow chart, because they do some rather neat things here. So, number one, titanium is found in the form of titanium dioxide. Now, this is commonly known as rutile. Sometimes called ilmenite, depending on the rock it's actually in, but rutile is the most common ore for titanium. Yeah, rutile. Now, the first thing they want to do with titanium is they want to react it. They wanted to put it in the blast furnace, and they did. They tried it. They added the rutile to the blast furnace to react it with carbon. Now, the problem is something rather odd happens. It doesn't form titanium metal. It forms TiC. This is otherwise known as titanium carbide. Titanium carbide. And this was a disaster because it's not titanium. It's a black, grayish black solid, which is not metallic. Yeah. I'm tempted to show you what titanium carbide looks like. Titanium carbide. It's a grayish black solid. You can make materials out of it. There you go. There you go. It looks like that. It's a grayish black solid and not especially useful. You can add it in small quantities to stuff, but it's not especially useful. Yeah. So what we want to do is we want titanium metal. We want the silver shiny stuff. Yeah. We want these things. Yeah. That's titanium, by the way, with a small amount of titanium carbide added. But we want pure titanium. We don't want this horrible gray powder. So we can't use carbon. Yeah. Problem. Titanium bonds to carbon. Problem. Sadly. Right, so we can't do that. So what we now need to do is we now do a different process. We take titanium oxide, rutile, and we react it with chlorine gas, nasty chlorine gas, solid titanium oxide, chlorine gas, and a small amount of carbon. Now what happens is the carbon acts as an oxygen mop. So what now happens is you form tickle, and carbon dioxide. The chlorine binds to the titanium and it becomes a liquid. So I'm going to balance that, by the way. There we go. That makes more sense. So the carbon is, by the way, it's done in 2 stages, just so you know. Yeah, just for your information. Yeah, in the flow chart, you had TiO2, and then we added that to chlorine gas in chlorination, adding it to Cl2, to chlorine gas. And then in a second step, so the first of all, they add the chlorine. Step 1, add Cl2, and then S1, step 1. And then they follow it moments later in step 2 with carbon. Step 2, add carbon. Yeah. So they actually do it in 2 stages. And in comes here, this becomes tickle, but then the oxide type TlCl4, and then the oxygen, which becomes loose, then picks up the carbon to form CO2 in the second reaction. So we've now got tickle. What we now do, so that's stage 1 in terms of my flow chart. Yeah, I am doing a flow chart, I promise. I'm just trying to zoom out. Yeah. So we took it, we had stage 1, TiO2, we add it, yeah, to chlorine, yeah, add Cl2, and you form titanium tickle, and then you get CO2 as a byproduct. Now the CO2 is very hot, by the way. This whole process is done at about 1,000 degrees Celsius, crazy high temperatures. Now what they actually do is, the CO2 comes out hot, and what they actually do is they recycle the energy. Yeah, they use the hot CO2 to heat this chamber. Yeah, the hot CO2 is used in a heat exchanger, yeah, to recycle energy, recycle heat, saves money. Yeah, now we've got tickle. Now what we do is we now need to extract the titanium. So now what we're going to do is we're going to do the next reaction. We then take tickle, and by the way, now here comes the reduction. We now add magnesium metal. The magnesium metal reacts with it to form magnesium chloride and titanium. And the equation, I need 2 of those and 2 of those, and I'm done. So I've now got titanium solid. You can use sodium metal, by the way. You can use magnesium or sodium as a reducing agent in this particular step. And I think actually sodium's now used more than magnesium. If actually updating my chemistry, I'm pretty sure that actually the sodium is now used more commonly. There you go, 4 of those. And that comes out as a liquid. The titanium comes out as a solid. And so this is the reducing agent. This is the red agent, reducing agent. Yeah. And we're producing pure titanium metal. So just so you know, it's gaining 4 electrons. If you want to know what's going on, the titanium is in a +4 charge state, gaining 4 electrons from the sodium to form titanium metal. Yeah. Anyway, so cool processes. They're very different from each other, which is why they like to use it. In my flow chart, we now put it into this chamber here, and we now add sodium metal. Sodium metal, lots of it, and that then produces titanium, and what comes out as a byproduct is sodium chloride. Add Cl2. That's a better way of doing the flow chart. Add in sodium metal. How cool is that? That's better, isn't it? I like that. Yeah. Now the sodium metal, of course, is recycled. Sorry, the sodium chloride. The heat is recycled. Yeah, they then actually run that through electrolysis to get the sodium metal back, but they actually recycle it. But it is quite a cool process. I'm going to actually set you a homework to watch some videos. Finally. Right, I've only got one more thing in my lesson to go now, folks, and that's alloys. And then I'm finished. Right, alloys. Okay, really easy for Edexcel. Yeah. Pure metal. Diagram. Pure metal. All the atoms are the same. Let's go for, I'm going to go for a classic. Here's iron, iron, iron. This is pure iron. The atoms are all the same size, and they form in layers. Bullet point number 1, all atoms same size. Same size. Forms in layers, and those layers can slide. Now this makes pure metals very soft. Now I'm not talking about like plasticine soft, not talking about like cuddly toy soft. I'm talking like, you know, that they're still really, really strong, but you know, they're not as strong as they could be. Now an alloy is a mixture. Alloy is a mixture of metals. Now, by the way, there is one exception to this, which is you can also add carbon into it as well, because it can behave like a metal in an alloy setting. So I'm actually going to put an alloy, comma, a mixture of metals or carbon. So just to show you two, so the first one is iron, and then a tiny atom of carbon. Carbon's tiny compared to iron. Now what this does, is it disrupts the layers. Yeah. So atoms, different sizes. Layers, disrupted. Can't slide as easily. What that means is the metal's strength now increases. Yeah. So alloys, it's an allotrope of carbon. Finally, malleable. Graphite can slide. Yes, graphite can slide, but it's very different. Yeah, the exception is an allotrope of carbon like diamond. Yes. I wouldn't get into those. I'm going to be teaching you those relatively soon, so try not to think about them too much at the minute. So the alloys are not complicated. It's a very simple process. Yeah, and I'm actually going to leave it there today because that's all I need you guys to know. So alloys are designed to increase the strength. You can also add other metals in to stop other properties. So stainless steel, just to show you what stainless steel looks like, because it has another thing in it. They add chromium. Stainless steel. I want particles. They're going to give me something with a picture? No, they're so not going to, are they? They're not going to give me the diagram I want. Of course they're not. Of course they're not. So stainless steel, just for those people who are interested. Stainless steel. The diagram is Fe, and then chromium. Now, chromium is larger. It's larger than iron, and carbon, which is very small. Now, don't get me wrong. There are only a few chromiums in there. All of these are Fe's. Yeah, there are only a small number of them, but the chromiums do exactly the same thing. Different sizes, but now the chromium, I'm going to color code this. Chromiums. Yeah, these give it the property of stainless. They don't rust anymore, or at least it slows the rusting process. The iron, of course, is the darker gray. Yeah, these are the irons. These are the iron ones. And then the black ones are the carbon atoms, disrupting the layers even more, increasing its strength. So stainless steel, the chromium stops it rusting, just kind of cool. But the same process applies. Disrupting layers can't slide as easily, making it stronger. That brings the lesson to an end, folks, and your test is tomorrow. Right, I've got to remember to turn back on my camera. It may crash my computer. Apologize if it does. It looks like it's survived. Winner, start cam. Is it going to do it? Hey, it is. There we go, guys. Right. I will stop screen. There we go. I will leave you guys be. Have a nice rest of your day. And your test is tomorrow. I'll see you guys then. Take care, guys.